Assalamualaikum warahmatullahi wabarakatuh. This is group 23 and we will present about assignment 3 and assignment 4. I will go with introduction first. My name is Noshani Ramita Majamil. The schematic diagram assignment 3 visually represents the electrical system layout for both MOS and office. The wiring system and cable selection assignment 4 ensure the schematic is practical, safe and efficient. Both assignments together create a comprehensive and robust electrical installation design for the MOS and office. Next, I will talk about overview of assignment 3. Develop a schematic diagram for all distribution board in both MOS and office. It includes lighting, power, air conditioning, subsys board SSB, power factor correction board PFC, and main fuse board MSB. Consider future development by allocating a 20 to 30% spare capacity. Assumption: actual power factor is 0.75, the target is 0.95. Design scalable and efficient system for both MOS and office environment. Okay, next is overview of assignment 4. Decide on the wiring system for the electrical installation. Select sub-main cable for each distribution board. Ensure a 4% voltage drop assumption from the voltage supply. Distance from FSB to SSB for MOS is 100 meters. Ensure compliance with relevant electrical standards. Adapt design to meet the specific needs of both MOS and office. Okay, next I will talk about objective for assignment 3 and assignment 4. Objective for assignment 3 is to develop detailed schematic diagram for electrical system in both MOS and office. And objective for assignment 4 is to decide on the wiring system and select suitable cable for each DB in the MOS and the office. Next, for the problem and solution for overall assignment. The problem is issue. The main switchboard MSB is a critical component and ensuring the voltage drop does not exceed the 4% limit over long distance. Particularly from MSB to SSB is challenging. This can affect the reliability and efficiency of the entire system. The impact if exceeding the voltage drop limit can lead to inefficient power delivery, reduced equipment performance, and potential safety hazards. This is particularly problematic for high-power equipment and over long cable run. And for the solution, cable size adjustment. Re-evaluate and possibly increase the cable size to handle the load within the voltage drop limit. Selecting cable with larger cross-sectional area can reduce resistance and voltage drop. Distribution point. Introduce additional sub-switchboard SSB or distribution point closer to the load center to reduce distance from MSB to the distribution board. And that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Iwanina Zafira binti Karabizan. I will explain assignment 3 for distribution board and sub-switch board. The first step is we need to calculate the current design IB. For single phase, we use total maximum demand divided by 230 times power factor. For three phase, we use total maximum demand divided by set3 times 400 times power factor. We assume that 20% from total load is spare. For sensitivity, we use residual circuit device guides. For TB lighting, single phase and three phase is 100 mA. For DB socket single phase and three phase is 30 milliamp. Then for MCCB rating, we refer datasheet. For datasheet MCCB and SSB, we use Sasin datasheet. For MCCB, we use frame B, and for SSB, we use frame C. Okay, the next is the example of Excel table for DB and SSB. For distribution board, we have 11 unit of distribution board. As you can see, for SSB1, we have 4 distribution board. For SSB2, we have 4 distribution board. And for SSB3, we have 3 distribution board. The first step is we copy the value of total connected load from the Excel of assignment 2. Then, we calculate the 20% of total connected load, and then we sum up the total connected load and 20% of total connected load. We also copy the value of maximum demand from Excel assignment 2, and then we calculate the 20% of maximum demand, then we sum up the total maximum demand. Then we can calculate the design current IB by using the formula that I showed earlier. Okay, and then we can determine the MCCB rating by referring the datasheet and the sensitivity of RCCB by referring the table that I showed earlier. For sub-switchboard, we have 3 sub-switchboard. The first step is we calculate the total connected load, then total maximum demand, and then design current, and we also determine the MCCB rating. We use the Tenaga Nasional Scheme to comply with maximum demand loads and supply scheme. As we can see, for DB Aircon, ground floor and first floor for office, we split to 2 to comply with the scheme. And then, after calculating all the value in the Excel table, we can draw the schematic diagram of distribution board. The first one is lighting distribution board, the second one is socket distribution board, and the third one is aircon distribution board. And then, same as for subswitch board, we just include the value from the table and put in the schematic diagram.
Okay, hi. My name is Nina Fadila binti Muhammad Nasir, and I represent for the SM3 for the part of main switchboard and power factor correction. So, next, you can see for the first table, this example of Excel that we use at SM3 to calculate the current design for IB at main switchboard. For the rating that we select for current MCCB is 315 ampere and used for pole. And also is we just use an MCCB because it's not already exceed 400 ampere to use MCB. And next, this example of this datasheet that we use for main switchboard. This datasheet from the SASIN, and also we use frame D because the rating current is too high. Okay, next for the problem at main switchboard is the main switchboard face several issues such as for the first part is overloading and overheating can lead to potential failure and fire hazards. And the second problem is poor organization where is difficult to manage and maintain, leading to troubleshooting issue. And also, the third for is inadequate protection, where With insufficient circuit breakers or fuse can result in electrical faults. And lastly, space constraint limit the potential for feature expansion. And for the solution of the four problems that I mentioned before, the first is with the overloading and overheating, we can we can propose the solution with provided proper load calculation because it is essential to ensure adequate sizing and prevent overloading. So at the assignment 3 that we made a calculation for the MSB and is started from DB, load, DB and SSB, we have to calculate properly and slowly to make the calculation good have a good have a good answer. And solution for the problem 2, an effective layout with organized arrangement allows for easy access and maintenance. And for the third problem, we can install an appropriate protection device such as circuit breakers and fuse for ensures the safety. And lastly, for the problem space constraint, we can scalable design should be implemented to allow room for feature expansion. And lastly, for the impact of the all problem and solution, uh, implementing this solution for the main switchboard results in increased safety. For the increased safety, reducing the risk of electrical fires and failures, and also its enhanced reliability is achieved through the easier maintenance and troubleshooting, and it's also improving uptime. And next, cost saving are realized by avoiding costly downtime and repair. So the money can save uh, with the maintain the repair if breakdown. And lastly, a scalable and feature-proof design accommodates features electrical load increase. And this is an example of schematic diagram that we made at assignment 3. And also at this MSB, we provided a protection device. And also at this MSB, we use OCEF, EMT for the relay. And next is for the power factor correction. And the first problem that we face at this PFC is low power factor. A low power factor leads to increased electrical losses and higher electricity bills. And next, for the voltage drop, is reduce the efficiency of electrical equipment. And next, for the harmonics, it cause distorted waveform and can damage sensitive equipment. And also, lastly, the other problem is under or overcompensation due to incorrect sizing of PFC equipment leads to inefficient operation. And for the solution of all the problem that I mentioned is first, for the power factor correction, correct capacitor sizing based on accurate load analysis can improve the power factor. Next, second, harmonic filters should be used to mitigate the effect of harmonics. And third, implementing automatic PFC system allows for dynamic adjustment of compensation based on load requirement. And also, lastly, for the regular maintenance is crucial to ensure the power factor correction equipment is functioned correctly. And for the impact of the perfect correction problem, the benefits include lower energy costs due to reduced power losses and improved efficiency. And next, second, improved equipment lifespan is a result of reduced stress on electrical components. And next, lastly, better voltage regulation ensures stable operation of equipment. Compliance with regulatory for power quality is also achieved. And next, I will show for the example of schematic diagram. Before I show the example of schematic diagram, for the first, this calculation for perfected correction, when we have to calculate from the QC, and after that we have to find the QC new and also refer table. And for this calculation, we have to refer the table of datasheet we share to find the capacitor. And lastly, this is a schematic diagram of perfected correction. So that's all from me. Thank you.
Assalamualaikum. My name is Nurizati binti Nurizan. Today I will present to you about assignment 4. Assignment 4 is include the selection of cable type and size and voltage drop from load to distribution board to subswitch board. The project flow begin with draw cable line from chosen load to distribution board, then measure the draw line. Third, tabulated the value in Excel. Fourth, calculate the current. And 5, refer suitable table for cable size. Then lastly, determine the cable size and type. This is the schematic diagram of distribution board. As we can see here, this is the size cable that we choose from the calculation we get in Excel. This is the flow of calculation for cable selection and voltage drop. First, the current rating of cable. To determine the current rating of the cable, the equation should be used is maximum demand times 1 over correction factor for ambient temperature times correction factor for grouping of conductor times correction factor for thermal insulation times correction factor for cables. Then we can choose the cable size. The selecting cable size and type requires careful consideration of maximum demand current, installation environment, and safety standard. The cable size we can choose is from the table for D1A and for D1B. Next, the cable length. Measure the length in meter at load drawing layout where the SSB and DB are located. Fourth, cable voltage drop. The selected cable sizes are appropriate given the provided lengths and loads. Adjust cable size or length if calculated voltage drop exceeds 4%. Then lastly, cable type. Cable type is determined based on the types of loads used and the total current requirement. This is the flow of calculation for cable selection and voltage drop. Example, we choose at ground floor. The maximum demand current we get from previous assignment is 3.82 ampere. Therefore, the correction factor for ambient temperature we assume as 1 as well as CA, CG and CI, also CD. Then we can find the current. The current is equal maximum demand, which is 3.82 over 1 times 1, which is CA, CG, CD and CI, equals to 3.82 ampere. After we get the current, we can find from the table for D1A, we can get the cable size, which is 1 millimeter. After that, we can find the voltage drop. Voltage drop is equal to 4.4 millivolt times cos 31.79 degree times 3.82 times cable length, which is 49.24, equals to 1000, and the answer is 0.70 volt. After that, we can find the voltage drop. The voltage drop is the 0.70 over to 230 because of single phase times 100% equals to 0.31%. The problem that involved is the cable size that determined by the computation is very small. There is less than 5% voltage loss. Then because of this issue, we choose a different size and kind of cable. Select a big cable size than used before to
Make sure the percent of the voltage drop is not less than 5%. Next is the economic decision. Larger cables are more expensive per meter than choosing a cable size that minimizes upfront cable size that minimize without compromising on performance is crucial. Uh, Energy losses. Smaller cables can lead to higher energy losses due to resistance, which increase operational costs over time. Larger cables, while more expensive initially, can reduce energy losses and save money in the long run. The voltage drop make larger cables have lower resistance, which reduce voltage drop over long distance. This can improve the efficiency of the electrical system and ensure that devices operate within their voltage requirement.
Hi, my name is Noor Fatini Aina and my matrix number is 221,092,205 and today I will present about main switchboard to sub-switchboard cable type and size and power factor correction bus bar. The steps in determining the cable size from MSB to SSB is first by draw the cable line from MSB to SSB, then the line are measured. The IT value were calculated, then possible cable size were determined by referring to table 4D1A and 4E4A. The cable voltage drop is calculated by referring to table 4E4B. The size of protective conductors are determined based on MSIEC 60364-554. The size of cable and protective conductor is determined when the voltage drop is less than 2%. The type of cable selected for SSB1 and SSB2 are PVC, while thermosetting type were chosen for SSB3 due to 100 meters distance from SSB3 to MSB, which we decide for an underground installation for the cable. The size cable for all SSB is as shown. Bus bar rating for power factor correction were determined based on MSB design current. The steps in determining the cable size from MSB to SSB is first by calculating the MSB design current. Then the bus bar amperage rating were determined using bus bar data sheet. For assignment for conclusion, the precise cable sizing ensure that the system can handle the expected loads without overheating, thereby preventing potential fire hazards and ensuring the longevity of the installation. The minimization of energy losses through correctly sized cables contributes to energy efficiency and reduces the carbon footprint, aligning with contemporary concerns about sustainability and environmental impact.